In the past video, we defined graphs. In this video, we are going to present some of the important terminology related to graphs. Let's begin. Let's suppose you are given a graph v comma e and you want to define the neighborhood of a particular vertex v. So we call adjacency set, and the adjacent of v is all the nodes or vertex of the graph G that are connected to that node V. Continuing, we also define the degree of node V, which is basically the size of the set of adjacent of V. For example, you have this graph that we have been using as our running example. Adjacent A is the set C, B, and D, and adjacent of D is A and B. Now if I apply the definition of degree on A, we see the adjacent A has 3 elements, therefore the degree of A is 3, and similarly degree of D is defined to be 2. Now let us ask ourselves an important question. Is it possible that an edge can have both elements to be same? Since edge is a set of size 2, you cannot have an element repeating 2 times. So therefore, the way we have defined our graph, the self loops are not allowed. If you have this, then what do we say about B? If you sum the degrees of all the nodes, then what is the sum? Since each edge is counted twice in the degree counting, therefore the sum of all degrees will be twice as the sum of all edges. Now let's continue. Now let's define paths, simple paths, and cycles. Again, we are given a graph v comma e, and let's suppose n is a non-negative number. A path is defined as follows. It's a sequence of vertices v1 to vn such that every consecutive vertex belongs to set E. A simple path is a path in which no node repeats. v1 to vn is again a sequence, and no vi is equal to another vj. Now, extending this definition, we define cycle. Cycle is from v1 to vn, where you have v1 to vn minus 1 is a simple path where there is nothing repeats from v1 to vn minus 1, and the last element is the same as the first element, and this is called a cycle. Let's look at an example. A, B, C, A, D. A, B, C, A, D is a path, but not a simple path because the node A is repeating. ABD is a simple path because no node repeats. ABDA is a cycle. ABDA is a cycle because ABD nothing repeats, and A, you start with A, you end with A. Now let's ask 2 interesting questions about this. Can there be an empty path? Okay, let's suppose n is equals to 0. Then what does it mean? If n is 0, there is an empty sequence. So this can be called a path. If n is equal to 1, of course there's no edges involved, but you can have a path of length 1 node. Let us define subgraph. Let's suppose you are given a graph v comma e, and a subgraph is v prime comma e prime, such that v prime is subset of v and e prime is subset of e. Very simple concept. Similarly, we also have defined a removing set of nodes from a graph G. Given a graph G, G minus v prime is removing nodes v prime, and whatever is left is a subgraph of G, and it is written G minus v prime. Please notice this notation. If you remove some set of nodes, then what happens in certain edges may have this situation. Half of the edge is still in the graph, another half has been removed. So then we have to remove those edges also. Therefore, we need to write a slightly complicated manner to say that all the edges which are dangling must be removed. Let's consider an example. The left graph is a subgraph of the right graph. Look at this graph, it has one extra edge. Now let us define one more concept, which is called connected graph. In the connected graph, every node is reachable from another node. The idea is that from V to every other node V prime, there is a path. A connected component is the parts of the graph which are connected, but they're not connected with each other. So you need to take every maximally connected subgraph of G and take their set. This is called connected components. Take this example of a graph which is not connected and it has two connected components. Now let us define something called a complete graph. Again, you are given a graph, and a complete graph simply says that from every node there is an edge to every other node in the graph. This, for example, here is a graph. We have 4 nodes and all nodes are connected to every other node. This ends the introduction to some basic concepts about graphs. Next we will define tree using the concept of graph, and now we will not be using a recursive definition of trees. Please look at our next video.